Okay, I see a funny symbol over here. It's a symbol that we use in the United States, by the way. It's the greatest integer function, and it denotes the largest integer that's less than or equal to x. There's a footnote over here. Let's go to that footnote. Computer science often refers to this as the floor function, and the floor function in a large part of the country is written this way over here, all right? It's an integer not larger than x, all right? In the C language, we call it the floor. It's also called floor in Python, at least in my version of Python. All right, so they say the floor of minus pi, and pi is about minus 3.1 something, which is minus 4. Makes sense over here. They go on to say there's a function f of x defined between 0 and 2, and they say this is the function over here. They go on to say that f of x equals 0 otherwise, by the way. So it's only defined as f of x equals 3/4 to this floor of log base 2 of x when you're between 0 and 2, otherwise just 0. They go on to say that, f of 1/2 would be 4/3. Let me just check that out, by the way. So f of 1/2 would be 3/4, and it's going to be the floor, and that's going to be log base 2 of 1/2. Well, that's not a bad problem, by the way, just 2 to the minus 1, so it's going to be minus 1. And the floor of minus 1 is minus 1. All right, so what do you get? You get 3/4 to the minus 1, which would be 4/3. Makes sense, by the way. Again, sometimes I wonder what the question is. The question to me is difficult. They're asking for this over here. All right? That's an integration problem. Now, I got to answer that. I don't think I could find that guy's antiderivative. I'd be shocked if I could, by the way. So I'm thinking it might be a visual problem. So I want to start to visualize the problem by going to the whiteboard. All right? And as I go to the whiteboard, certainly I got to think about it. And the first thing I got to think about, I got to think about the log function. And the log function is base 2 of x, and the x is between 0 and 2. So if I were to visualize this over here, I'm going to say it looks sort of like this. And this is the number 2. Oh, it's number 1. And I'm looking at this over here, and I'm going to say the range of this is the domain, by the way. The range of it, well, it's going towards minus infinity, and then it goes up to, well, at 2, that would be equal to 1, but it's not going to touch the 1. All right? So the next thing I got to start thinking about is the floor of that. I'm thinking about the floor of this thing over here. All right? So I got to start thinking about it. And the way I think about this, I think about intervals where this thing's going to jump. So it'll be between 1 and 2. That's an interval, by the way. It's going to fall to 1. I'm 0, by the way. All right, put this over here. This will produce a 0 in the floor. And this is going to be the x's. All right? And then I go the next one. And someone says, I wonder what the next one is. The next one is going to go between, well, it's going to be 1 and 1/2. And the floor of that would be minus 1. And then what do? I go between 1/2 and 1/4. You notice I'm just picking powers of 2's, by the way. And someone says, what are you doing over here? This is 2 to the 1. I'm sorry, 2 to the 1. This is going to be 2 to the 0. And then I get, 2 to the minus 1, 2 to the minus 2, blah, blah, blah. That's all I'm looking at. What's this floor going to drop to? Minus 2. So forth and so on. And the next one, let's see, 1/8, 1/4. That's going to drop to minus 3. I think you get the idea of what's happening over here. All right? So then, if that's the floor, I'm really looking at f on those intervals. And I'll put this one over here. And I'm starting to realize this is going to be a set of rectangles. There's going to be heights, and there's going to be bases. And the first rectangle I'm going to get is between 1 and 2. Right? So I'm going to talk about the heights first. The heights are going to be 3/4 on the first interval. The height of the function would be 3/4 to the 0. The next one is going to be 3/4 to the minus 1. The height's actually getting bigger, by the way. The next one's going to be 3/4 to the minus 2, yada, yada, yada. Now I want to put the base down. And I'm going to write it. The first one's going to be, I got to be careful here, 2 to the 1 minus 2 to the 0. That's its base, by the way. I'm just looking at this over here. I'm going to put things in powers of 2, by the way. 2 to the 0 minus 2 to the minus 1. That's that base. What's going to be? 2 to the minus 1 upper minus 2 to the minus 2. I think I see a pattern. All right? So let me write this one over here for you. It's going to be the base of the rectangle times the height of it, or the height times the base. Let me start talking about the areas now. It's infinite, by the way. So it's going to be 3/4 to the 0, 2 to the 1 minus 2 to the 0, plus 3/4 to the minus 1, 2 to the 0 minus 2 to the minus 1, plus 3/4 minus 2, 2 to the minus 1, 2 to the minus 2, minus 2 to the minus 1. And I'm going to say that's a definite pattern to it. So let me write this down as a summation, the sum. I'm going to use index j equals 0, and you may wonder why I'm doing that. I'm seeing a 0 in the problem right over here, and that's going to go off to infinity. It just keeps going and going and going. So it's going to be 3/4 to the j, and then I see this product over here. So it's always a problem doing that, by the way. So I'm going to say, let me see if I did that right. Oh, you know what? It's minus j. Sorry about that, because I'm seeing 0, minus 1, minus 2. And by the way, I'm seeing 0, minus 1. Whoops, made a mistake over here too. Let me correct that, by the way. So let's see, it's going to be, let's see, 1, 0, 0 minus 1, 2 to the minus 1, minus 2 to the minus 2. Yeah, 1/2 minus 1/4. Yeah, let's put this down. 0 minus 1 minus 2. Okay, let's put this down. So I'm going to put down 2 to the minus j. By writing it as some of these, I can do it, but I can certainly write a sum down, by the way. And let me do the other one. I'll think about that over here. So it's going to be 2, 1 minus j. It's one more than the other, by the way. I got troubles now. And my troubles is figuring this thing out. So someone's just figuring what out? I'm trying to figure this thing out over here. And the way I'm going to do that, I'm just going to rewrite it a little bit. All right? I'm going to write this. I'm just going to write it down as 4/3 to the j. And then I'm going to write the next guy down as 1/2 j minus 1 minus 1/2 to the j. I'm going to keep moving. I'm going to write this as 2 to the 2j and then 3 to the j. Over here, I'm going to write this as 2 to the j. I got to be careful now. So, I'm going to get 2 minus 1 here. Yeah, it seems right. Let's keep moving. So we get 2 to the 2j over 3 to the j, and this will be 2 minus 1, which is 1, and 2 to the j. Well, things are shaping up. I'll tell you why. I'm going to use rules of exponents, and I get 2 to the j over 3 to the j. So this sum turns out to be pretty simple, by the way, and it's going to be j equals 0 to infinity, and it's going to be 2/3 to the j. All right? So that was a little bit of work, wasn't it? And I'm going to say it looks geometric now. And let me get my eraser out. Get a bigger eraser out. That's my scratch work. And I'm going to say it's a sum, geometric sum. Let me just remind you what that sum looks like. It's 1 plus 2/3 to the first power plus 2/3 to the second power, yada, yada, yada. It's geometric in form. 1 minus 2/3. I can multiply top and bottom by 3. You get 3 on top. Bottom, you get 3 minus 2. And, I'm sorry, 3 minus 2. You get 3. 3 minus 2 is 1. You get 3. What's the area going to be? Area is going to be 3. And we're done. This was a tough problem, by the way. I found it to be difficult. Thank you.